Hello everyone, today we're talking about finding limits algebraically, section 12.2. Okay, so in this section we're going to have a lot of limit laws and some special cases. So they're here and they're also provided in the PowerPoint, so if these are not very visible you can go ahead and copy them down from the PowerPoint. Pretty self-explanatory, allows us to break up sums inside the limit to the individual limits, difference inside the limit to the individual limits, and I think the other ones are pretty self-explanatory. So as we go through the examples, I'll refer back to this, but I'm not going to go through and explain each one because I think they're pretty self-explanatory. Again, if you have limit of some constant as x approaches a, then it's just a constant. So if you just have a limit of a number, like limit as x goes to a of 1, then your limit is just 1, right? It's always going to be 1. If you have a limit of just x as x goes to a, then obviously our limit is a. And then same with if it's a x to a power, then it's a to a power. If it's a square root of x or nth root of x, it's the nth root of a. And then finally, if a polynomial has a in the domain. So we talked about in the previous chapter, or the previous section, where we couldn't just look at the table, right, and see if that limit existed at a certain value, because in the table that value was not there, right? It wasn't part of the domain. But if that number is in the domain, like if we're approaching 2 and 2 is part of the domain, then we can just substitute that 2 in wherever we see an x, and that'll give us our limit. And you'll see an example of that. Okay, so first we have graphs f and g, and they want us to compute these couple limits. So I have a limit, or I have an addition inside my limit. Using my limit laws, I'm allowed to break that up. So I get limit as x approaches 1 of f of x plus 3 times. So I'm using 2 rules here. I use the addition where I can break it up, and then I've also used multiplication, constant multiple law, where if I have a c inside the limit, whatever constant, whatever number we're multiplying the limit by, I can pull it out in front and multiply it by the limit. So I use both laws there. So 3 times limit as x approaches 1 of g of x. Okay, and if you see as x approaches 1 on f of x, so as x approaches 1, my y approaches 3. So let's see if I can find this room here. So this will approach 3, and then 3 times as g approaches 1. So as x approaches 1, my g function is going to approach -1. So I get 3 plus -3, 0. So that first limit is equal to 0. Okay, let me go ahead and move this down. Second limit they wanted, we're going to have to use the product rule. So we're allowed to pull these 2 limits of function f and function g and then multiply the limits of each. So that gives me limit of f of x as x approaches 0 times limit of g of x as x approaches 0. So as x approaches 0, you'll see the limit of f. Well, as x approaches 0 from the left and the right, they are not meeting at the same point. So this does not exist. And my limit of g as I approach 0, well, I get 0 because it's approaching 0 from both sides, but I can't multiply something by something that does not exist, so this limit does not exist. Next, we had to use the quotient law. So we're, again, self-explanatory. If you have division inside the limit, you can break it up into division of the limits. So that just breaks it up into limit x approaches 2 of f of x divided by limit as x approaches 2 g of x. And as x approaches 2, f of x is going to be 4 because it approaches 4 from both sides. So that's 4 divided by, as x approaches 2, g is going to approach a y value of 0. So this is undefined. Cannot divide those limits since the limit as x approaches 2 of g of x is 0, cannot divide by 0. And finally, we're allowed to take the limit first, then square it. So let's take the limit as x approaches -1 of g of x. And then we will square that whole limit. So as x approaches -1, g of x approaches 1, right? So y approaches 1, so we get 1 squared. So that limit of as x approaches -1 of g of x squared is just 1. Okay, so that's using a graph and our limit laws to find the limits. Now we want to just evaluate these limits. Like I said, this is going to use direct substitution because as long as the limit that we're looking for is part of the domain, I can just plug it in. So I'm going to quickly go ahead and graph this and show you that x equals 2 is in the domain of this, so then we can just use direct substitution. Okay, so if you look at the graph, right, definitely going to include, and even if you look at the table, includes x equals 2. So our limit is just 3. So if you plug a 2 in wherever you see an x, you come back with a limit of 3, and that's the limit. All right, it's going to approach 3 from the bottom and the top. Likewise here, if you plug a 1 in, you're going to get a value, right? So 1 is part of the domain. 1 exists in the x values of that function. So I can go ahead and substitute it right in. So that's 2 times 1 plus 1 over 3 times 1 plus 1. And so that gives me 2 plus 1 over 3 plus 1, which is 3/4. And if you go ahead and, I'm sorry, that's 2. This is a -1. So that gives me 2 plus 1 is 3. This gives me, and that's not a 1, that's a 2. Okay, so then this gives me 3 minus 2 is 1, so my answer should be 3. There we go, now we got the correct limit. Okay, so again, if you went through and graphed this, you would see at 1 you're going to get 3, and both sides are going to approach 3. Okay, the last one. I'm going to go ahead and graph it and show you what happens at 2. So as x approaches 2, everything looks good, right? Looks like we just have a straight line. However, if I go to my table, you'll see that at 2, there's an error. Okay, so it doesn't necessarily mean that we do not have a limit. It's just saying that the number 2 is not on this function, right? When x equals 2, we do not get a y value back. However, as we learned in the previous section, there's definitely going to be a limit there when x equals 2 because it's going to be approaching the same value from the left and from the right. So in order to find that value, we're going to first need to factor. So if I factor the numerator is going to factor 2x minus 2 times x plus 1. And the denominator obviously stays x minus 2. So we can see here that since we have a common factor in the top and the bottom, that we just have a hole when x equals 2. So since these cancel, there's a hole there when x equals 2. So that does not mean it doesn't have a limit. It just means that the function is not defined at that point, but we will still have a limit. Because you saw as the graph went, they were meeting at the same point. So now I can go ahead and substitute it in and see that the limit as x approaches 2 of x plus 1, because I've canceled the other terms out, I'm really going to get a limit of 3. And if you go ahead and if you did a table of values just to make sure that below 2 and above 2 you're approaching 3, you'll see that our values will approach 3. So the actual limit of this is 3. Don't just go to your table and see that, oh, 2 is undefined, especially when it looks like a continuous line, there's probably a hole. So you're going to have to cancel a factor. Similar questions are like this, where we're going to have to cancel a factor. So you can obviously see that if you just plugged a 3 in the bottom, it'd be undefined, right? Because we'd be dividing by 0. However, there is actually a limit when x approaches 3. So I'm going to want to factor first. And that's going to be x plus 3, x minus 3, divided by x minus 3, which proves there's a hole there. And then I can just directly substitute in and see that as x approaches 3, this function is going to approach 6. Okay, so the limit is 6 there. Likewise over here, first thing I'm going to do is factor. And I get x plus 5, x minus 5. Now it may not always be nice, neat, perfect squares like that. You know, difference of perfect squares. So you may need to find the factor like in the previous one. But if you can see, if it looks continuous on the graph, so I check the graph, then there's probably a hole. Just like there's a hole here at 5. So now I can direct substitute and I get that this limit is 10. So as x approaches 5, y approaches 10. And finally, it just says to use a graphing device to determine if this limit exists. So here I've already graphed this function. And we can see that as x approaches 2, from the negative side, right, it's going to go to infinity. And so as x approaches 2 from the positive side, that's going to negative infinity. So since these are going to infinity and negative infinity, right, not the same point, obviously, so our limit does not exist of this function as x approaches 2. And hopefully by now we get the point that as long as both sides are not approaching the same value, then we do not have a limit for that function. So go ahead, try the example problems on the PowerPoint. Make sure you get those notes copied down for the laws of limits, and then we'll talk about it in class tomorrow.